So let's dig into pre-processing. What is the first rule of pre-processing? It is basically always inspect your data very closely at several stages. And this is go through your data in terms of the locations, have a look at all your brains at least once, visually inspect them. The second rule is actually follow the first rule. And these are rules taken from the Hutel book. The reason for this being that, in fact, sometimes we have data, and an estimated 10% in our data sets have this, where we have some artifacts that we might miss otherwise and then include in our larger data set. For instance, here you can see there's this sort of hole in the brain or a region in this brain where we have a signal dropout. And this could be due to for many reasons. It's typically just a calcification, and so there's no signal here for this person. But if you look at this brain more closely, you see that there may be other parts within that brain that have signal dropouts. So this is maybe a brain that we don't want to include because that's quite a large signal dropout here. And we ask you to do this, to look at your data very closely and report on what you observe, visually, simply, when you have a look at this. So we will show you how to make a video for each participant that shows in a very quick succession a timeline of how the scans were recorded. And you can see very large movements, you can see relatively small movements, and even, sometimes you see the eyes move, and sometimes you can even pick up some minor signal or actually quite large signal changes within the brain. And the reason for why we do this, for why we need to double check our data and visually inspect the data, is because it's become so easy to just run statistical analyses on this so that anyone can do this. And that's what the quote here is saying. Even the least experienced investigator can pre-process, analyze, and combine data across subjects without ever examining each subject's data. And that's still one of the most important steps, because you pick up problems in the data. Otherwise, you just might end up with false negatives or false positives within your data, which we don't want. Unnoticed problems can propagate into the final results of an experiment with potentially disastrous results. Well, one probably most disastrous result is the presence of false positives. So you claim that something is present, although it's not actually there. But it's also equally bad for you if you end up with false negatives. So something that you should have detected, for instance, in this region, SPM makes a mask based on all the subjects. So this region won't be in your final map. And you can test this. We'll go through this in the lab. Indicating that you actually have a dropout in your final data set here. And maybe this is one of the regions that you should be most interested in, right? It's somewhere around the anterior cingulate cortex, which may be an interesting region for a decision-making task. But again, we'll discuss this in the tutorials. So let's talk about pre-processing the data to improve data quality. And that concerns co-registration and motion correction, as well as slice timing correction. In fact, the most severe problem is the fact that problems move while they're being recorded. We're asking them to lie in a strange position as still as possible for about an hour, sometimes even a little bit longer. But we try to limit this to a maximum of an hour, and ideally just 45 minutes. And participants do a good job because we wedge them into this cage here. So this is the head coil, which allows us to record data from the brain. And we put a big headphone onto their heads. And then we take, in addition to this, we take foam pads that push onto the headphones and basically align the heads and lock it in relatively tight, right? So the headphones are there to protect the hearing of the subjects from the loud noises that the scanner makes. But this still gives a little bit of space to move around, but it reminds the subject to please stay silent. But there are different methods to keep the subject locked in. One is this rubber mask, which straps around the face. That's a bit extreme, I would say. Another one is a bite bar that is shoved into the mouth of the subject and keeps the subject in place, also a little bit extreme. So we use this method here. Head motion is the most serious problem for fMRI studies. So we want to minimize it, but if we can, then what we do is we remove the subjects. If the head moves, each voxel's time course will be derived from more than one brain location. And I'll show you this in a minute to illustrate how this looks like. So basically, we get these large signal drops or signal increases if we have a head move. The location of the scanner, the recording locations are absolute in space, not relative to the head. So when the head moves, you might lose a voxel at the edges, right, depending on the direction that the head moves, leading to either signal increases or signal decreases in these regions, just due to head movement. And we don't want this. So at the edge of the brain, signal intensity can change by a factor of 5 times or more if head movement occurs, right? And that's compared to less than 1% changes due to task-related brain activity. So we're working with relatively low levels of changes of interest, typically in the order of 0.5%, not even 1%. If we have motor activity, it can go up to 2-3% of signal changes between task on versus task off. But when it comes to neuroeconomics and we're interested in changes in value, then we're talking about much lower signal change intensities. So that's the level of signals, the very minute changes in signal level that we need to work with. And if the noise is larger than this, then obviously we have a very difficult time detecting this. And signal changes due to movement are not related to our experiment, and therefore obviously increase the noise level, making it much harder to detect real changes due to the task that we, as experimenters, ask our subjects to do. Okay, so as I said before, the scanner acquires images at absolute spatial locations and unfortunately not relative to the brain's position. So if the brain moves, then what will happen is each voxel's time course will be derived from more than one location in the brain. Let's have a look at this. So here we have this region here that's recorded from this slide. Then the head moves slightly, and then whoops, all of the voxels are shifted and no longer recorded in the same space. So after this movement occurred, everything else will be recorded from actually a different location. So here we're recording from, a very superior region, and then the subject moves, and all of a sudden you're very close to the the mid-cingulate type region here, just above. So that leads to a problem, right? Just to show you what this does to the data, let's consider this small blue box here. We're talking 1 voxel, right? So this box contains 3 voxels. So the length of this box is actually, in a normal experiment, is about 9 millimeters, 9 by 9 millimeters for a voxel size of 3 millimeters. It's a very tiny voxel, and the subject moves just a tiny bit, such that the box shifts by just 1 voxel to the left, right? This is the shift, and we can see this quite well here. That means that these values all of a sudden increase by, in this case, over 5 times the amount of signal that we have, and this will show up in the images, in the statistical images, as an increase in signal intensity, but it's only due to movement, and we don't want this. So a small head movement of approximately the voxel size between 2 to 4 millimeters leads to these large changes in signal intensity, and this is something we can actually pick up as rings around the brain of activation, right? This is movement simply due. This is activation simply due to movement, and you can see these activation rings. It's something you can check your data for now that you know it. Did you control properly for motion? if you see this, then most likely there's a problem with the way you did this. So we're considering motion due to a translation forward of 2 voxels at stimulus onset in one block, and the back of the brain will change from high to low intensity. If we're moving forward, then all of a sudden all of these voxels are no longer inside the brain, and it'll lead to a decrease in intensity due to movement, something we don't want. As a side note, a decrease in intensity is usually indicated in blue colors, whereas an increase in intensity is usually indicated in reddish or orange colors. And obviously, if we do lateral motion, so from to left or right, then you get positive activation on one side and negative activation on the other side, right? Depending on which way the movement is. But the good news is that if the movement is not so large, so we can deal with about 1 voxel size of motion, maybe up to 1.5 voxel sizes of motion, or 2, but no further than that. If it's more than 2 times the voxel size, so in a normal experiment, about 6 millimeters of movement, which is not much, right? If you think about lying still for 1 hour and you cannot even move 6 millimeters, then that's asking quite a lot from your subjects. We can detect it, and we can correct it if it's below that amount. And there are 2 types of typical head motion. Gradual, smooth movement within runs is typically well corrected, and you can see this here, for instance, on the y-axis. This is gradual movement. We don't have much problems in our algorithms to correct this, whereas abrupt movements like this one here, they are a bit harder to correct. But in this case, in the z-axis, this could actually be due to scanner drifts. So that is something we have to live with in some sense. Also note the axes here. So the y-axis is moving from sort of the back to the front of the brain. The z-axis is moving from top to bottom of the brain, and the x-axis is lateral movement from left to right. So luckily there are a number of things we can do to prevent head motion even. So there are experimental solutions, and that is to keep your experiment as short as possible, because people are more likely to move as time goes by. As their body starts aching and they become tired, they start moving around a little bit more. And also, if the experiment is boring and not entertaining, people will move more. What we're doing then is to have experimental runs that last somewhere around 4 to 8 minutes. Typically, they're about 8 minutes, to be honest, and that are self-contained. So that means they contain all the conditions that occur within the entire experiment, so that if you lose a run, you don't lose some of the conditions, and you can still analyze your data. This gets more difficult with complex designs, which is the reason why many times these runs are actually longer than 4 to 8 minutes. But we try to keep them as short as possible. We also try to keep the experiment as short as possible and limit it to under 1 hour. Sometimes there are deviations, but then these experiments become torture to participants, and we don't want to do that. It's best to then interrupt and ask participants to come back if this is necessary, and do this in 2 sessions. We also want to provide some time for rest between runs, where participants can then wiggle their toes a little bit, but without moving their head ideally. And we talk to them just a little bit to ensure that we're still there, and ask them how things are going. We can prevent head motion, as I mentioned earlier, using different types of devices. This is a bite bar here. That's not so nice, right? You can see the bite bar there as well. We simply just use the padding that's shown here on the sides. But there are also masks. This participant here also is chewing down on a bite bar, which limits the range of motion that a participant can have. But padding is the best. Padding such as shown here or here, or simple foam pads and mic and headphones work very well for us as well. And then after the scan, there's usually some residual head motion that we have to deal with. And we have algorithms for this in SPM that are called motion correction algorithms or co-registration algorithms that we can use. And the goal of motion correction is to adjust the images so that the brain is in the same position for every image. It basically takes a reference scan. Let's say it's the first one or the middle one of the entire series of scans that we've taken, or it could be the mean volume. You take an average of all of this and take the mean, and then you take. Let's go with the first one here. You estimate the deviation of every single following volume from the first one, and you record how much does it deviate. And you can do this because you have the edges of the brain and you have some landmarks within the brain that allow you to look at, well, how much does this image, so the second image, deviate from the first image. And then you can see by rotating the image what is the ideal combination of rotations that make these two images correlate at the highest level. That's basically what an algorithm does here. So it takes two images, the first one and the second one, and then looks at, well, how much does the first image have to be moved to be the best match to the, how much does the second image have to be moved to be the best match to the first image? And then you do the same for the third image. How much does the third image have to be moved to be the best match for the first image? And then you go through the entire series, 500 to 1,000, and estimate the deviation of each image in all of the directions that I showed you here. Let me show you again. In the X, Y, and Z directions, but also in the rotations in all of these dimensions, right? So there are 6 parameters that we're estimating that give us an idea of how much movement has taken place in these 6 dimensions. Then there are 2 steps. So this is called registration, what I just described, which is just estimating or determining the 6 parameters that describe the rigid body transformations between each image and a reference image. And I mentioned already there are 3 translations in the X, Y, and Z axis, and 3 rotations in the XY, YXZ, and the YZ planes. So again, we can move in all of these 3 dimensions, and we can also move in all of these 3 dimensions, right? So those head movements are all registered and then recorded. And finally, since we know then how much movement took place in all of these 6 dimensions, we can then take the original images and transform them. That's called resampling in SPM. So we interpolate spatially between each image according to the registration parameters estimated in the first step. So motion correction basically is a 2-step process. The first step estimates the head movements, which are shown here. So this is a participant that moved very little. You can see that there's a movement of less than 1.5 millimeters here, which is half the voxel size. That's almost perfect. And you can also see that the rotations are within the norm of less than 1.5 degrees. So the y-axis here is degrees, the y-axis here is millimeters. And we'll get this data from our data sets, and you'll get to do exactly this kind of graph in the tutorials. So now that we've estimated the movement, and this is the output from the realignment algorithm, we need to then use this output to correct head motion in the actual data set. So this is the next step, is to apply motion estimates to the data. So what we have then is we have an estimate of how much was moved, and we need to use this estimate to estimate the actual value of a voxel if no movement had occurred. So this would be something we can do this, and the algorithm will do this for you using interpolation basically. And it does this by estimating the values that voxels should have had the movement not occurred. So let's go back to this example here. What we have here is we have a movement to the left, and this is something that the algorithm has detected and has estimated. So we need to make sure that we get as close as possible to this voxel, and it does this by basically using an average of the surrounding voxels based on the motion estimate, so such that it comes closer to the value of 89 rather than 507 after the movement has been applied. But it doesn't know the exact value of the voxel at different time points, so it gives us an estimate of this. But this is a relatively good estimate, and this works. So there are two different, or there are many different types of interpolations, but I'll give you a note on how interpolation works. So there's linear interpolation, which is the simplest one. So the contribution of the final value is determined by how close the voxel is to the final destination, but there are more accurate interpolation schemes, such as spline interpolation. Let me show this how this works. So assume you have knowledge of some points, and these points are given at 1, 2, 3, 4, 5, and 6, and you know this. So let's say this is the spatial location or some representation thereof, and you have a voxel value that varies here between 1 and -1. And you want to estimate what is the point, what should be the value at 1.5, given the two values that you know of the surrounding voxels. And what you do then is, in the linear interpolation, you just simply take the average of these two. So you take this point here at 1.5, and you say the value now is this amount here. In a spline interpolation, you have a different function that estimates the intermediate values between 2 points. That's based on this more smooth and smooth curve here. And this is known to be more accurate than a linear interpolation, which is a little bit more simple and requires less computational power. And this is a way to be able to also estimate, obviously in a more complex manner, using the surrounding voxels and what we know about the motion in different directions, to estimate the value that a voxel should have had in the absence of any movement. There's a downside of interpolation, or resampling as it's called in SPM, and that is the more we resample, the more smooth the image gets. So we lose anatomical detail if we resample over and over again. But we are only going to resample once in our data set, so that is not such a big problem for us. It has to be mentioned, though, that motion correction is never perfect. So it's better to try to keep the participant as still as possible in the scanner. What I'm showing you here on the right side is the batch editor in SPM, and this is the realign, estimate, and reslice option that we're going to use in the lab. So we have the data that you read in here. So if you double click on this, or if you click specify here, then you can add the data to this, and we'll go through this step by step. And then you have a number of parameters that we define. You can see there that the interpolation here is a second degree B-spline, which is sufficient. And then these are the reslicing options. And what this does, basically, this will estimate the amount of movement, and this will then use interpolation to, as it says here, to rewrite the images and make sure that they're then registered in the correct space. And it gives it a new file name, which we will then be working perfectly. Good. Then finally, you can also correct head motion using MATLAB batch scripting. Something I just want to mention. If this is what you want to try, then you can use MATLAB batch scripting, and there are many tutorials on how to use this online. Let me know if you want to give this a go, and I'll give you the link to this.